Hi guys, and welcome to the third lecture of chapter 14. So far we've talked about what climate and climate change is, some of the ways that we study climate change and can predict and model its effects into the future, as well as how it reacted in the past. And for the third lecture in chapter 14, we're going to be going over a few of the impacts associated with climate change. So the impact that everyone generally associates climate change with is an increase in temperatures, and this is probably because the greenhouse gas effect inherently traps heat or thermal energy into the Earth's atmosphere and warms up the surface of the planet. And in fact, average temperatures have risen on Earth by about 2 degrees Fahrenheit or 1 degree Celsius in the last 100 years. However, it should be noted that most of that warming or most of that increase in temperature has actually occurred since 1975, which is much sooner than the entire 100-year time span that we just mentioned. In fact, we've experienced about 17 of the 18 warmest years on record. And if you're like me and you were born after 1985, you've actually never experienced a cooler than average month, let alone a cooler than average year. And while the different climate models that we talked about in lecture 2 have some variation, usually based on behavioral changes or policy implementations as to how hot the temperature will be by the year 2100, what they all have in agreement is that the temperature will rise between 2 degrees and 6 degrees Celsius, which is substantial. Also, if you note at the graphic down on the lower right hand corner of the screen, you can kind of see that most of this warming, the greatest changes in temperature, are going to be the poles. The average temperature increase in any given area is not going to be even across the entire planet. The areas that are warming the fastest are going to be the poles, and the areas that are going to see the least amount of warming are going to be the equator. So again, not only are we increasing temperature for the entire planet, but the increase is not universally or is not evenly distributed across the entire planet. So the next impact that we're going to talk about are increases or decreases in net precipitation. Remember how we talked about in the lecture 1 for chapter 14 that a warmer planet will speed up evaporation and also a warmer atmosphere will hold more water vapor. Now this inherently leads to changes in precipitation. Currently, precipitation has already increased about 2% worldwide in the last 100 years. However, it should be noted that these increases in precipitation are not evenly distributed, similar to the impact of temperature. In fact, a lot of places will experience far less rainfall. Basically, the areas that are already desert or semi-desert or arid areas will become more desert-like because they're going to be losing a lot of annual precipitation. And other areas are going to experience very heavy rainfall events, leading to things like flash floods and even erosion, as these areas which are not well equipped to handle large increases in water volume will see their soils be swept away. So it's actually very uncertain what precipitation is going to do or what precipitation trends will occur in the next 100 years as we keep increasing the temperature. Now, the trend could continue as is, where again, the precipitation has already increased, albeit very unevenly, at a rate of about 2% worldwide in the last 100 years. So we could see something very similar to the top scenario, or we could see one of the two bottom scenarios, where, such as in the bottom left-hand corner, water vapor could be transported and then released in huge amounts all across the globe, revealing very, very sustained increases in precipitation, or the water vapor could just stay in the atmosphere as the atmosphere gets hotter and hotter and gains the capacity to hold more and more water vapor, actually decreasing precipitation across the entire globe as well. So we actually aren't really sure what's going to happen as we continue turning up the thermostat. In some instances, you can have an uneven distribution of an increase in precipitation. You could have heavy sustained increases in precipitation, or you can have massive droughts and massive decreases in precipitation. We really aren't sure what's going to happen here. Now, the next thing we're going to be talking about is the increase in extreme weather, particularly the increase in frequency and intensity of extreme weather events. Remember that thermal energy is still energy, so heat is still energy, and heat is often converted into different forms. Basically, increased heat in the form of increased warm water and warm air is basically fuel for extreme weather events such as hurricanes, tornadoes, snowstorms, cold snaps, and heat waves, all of which we can readily expect in the near future. Now, the easy example that we can always reach for is the increase in frequency and severity of hurricanes, something that Panama City, as well as the entire Florida Panhandle and Gulf Coast in general, has seen plenty of. In the last 5 years, we have seen at least 8 hurricanes of Category 4 or higher in the Gulf Coast. Particularly fresh in everyone's memory is the landfall of Hurricane Michael back in 2018. Now, it's kind of easy to conceptualize how warmer water and warmer air can feed extreme weather events like hurricanes, which thrive on heat energy. However, it's less conceptually easy easy to understand how this heat can influence things like cold snaps and snowstorms. And again, this goes into the fact that heat is often converted into other forms of energy, such as kinetic energy in the form of wind that can power these incredibly powerful storms. Even if they are inherently cold weather storms, they still require energy in the form of kinetic energy or wind to enable their own motion, as well as the damaging impacts that they can unleash on other given areas. So remember, while heat energy is the energy that is primarily being added into the climate, that energy is often converted into other forms that can increase the severity of all different types of extreme weather events, not just the ones that thrive off heat energy in particular. So the next impact that we're going to be talking about is that of melting ice, particularly melting sea ice. And this is because, as we mentioned with temperature, the warming effects of climate change are going to be most severe at the poles. And Antarctica and the Arctic are losing ice at staggering rates. Study after study projects that the entire West Antarctic ice shelf is on the verge of total collapse, one of the largest glacier ice shelves in the entire world. This has huge implications for Antarctic as well as Arctic wildlife, particularly for organisms in the Arctic, such as polar bears, walruses, and many types of seals. These large mammals rely on summer sea ice or the Arctic sea ice in order to take a break from swimming and to rest and recover in order to begin the hunt again when they are feeling up to it. However, as this Arctic sea ice begins to melt and shrink in capacity as well as shrink in size, these organisms are beginning to have a harder and harder time finding different ice shelves or different ice islands in order to stop and rest. The result is often what you see below you, where you have this severely emaciated polar bear, which is literally starving and exhausting itself as it's constantly swimming and no longer able to find these stable ice shelves where it can actually rest and recover. And it also has huge implications for us as well. So remember that Earth's systems all connect and interact, and impacts in places even as far away as the Arctic and the Antarctic poles also can severely impact human societies as well as ecological systems all around the globe. And this is primarily going to be seen in areas such as the global food chains as well as some of the impacts of sea level rise, something that we'll be talking about in just a second. So sea level rise simply refers to the increase in sea level around the entire globe, normally as a result of global warming and climate change. Now, this is facilitated in two different ways. First and foremost are the melting ice caps. Melting ice caps transport water from the land to the sea. Note that icebergs melting don't actually contribute to sea level rise. This is because icebergs are already in the water, and it's sort of like how if you have a cup of ice water, as the ice in your water melts, it doesn't actually raise the level of water in your cup. Check it out sometime, it doesn't happen. The reason why is because that the ice inside of the water or the icebergs inside of the ocean are already displacing water. They're already pushing the water out of the way simply as a result of being in the water. So, and remember that ice is actually less dense than water. So as a result, when the ice melts, it actually reduces the total amount of volume of water in the area. It doesn't actually contribute to sea level rise. It actually shrinks the amount of the sea level down a little bit as the water is less and less displaced. However, ice caps melting, so ice that is on land and not in the water and melting into the water, contribute a net increase in water volume and do contribute to sea level rise. However, melting ice caps don't actually contribute to the majority of sea level rise. That actually happens as a result of something called thermal expansion. Basically, all matter, no matter what it is, will expand as it gets hotter and hotter. And this is the reason that you have those slats or those cracks in bridges or sidewalks. It's the reason they have gaps in them, simply to account for the expansion of that substrate or of that matter as it gets hot or as it gets cold. So it's going to expand and it's going to contract as it heats up or cools down. Water is no different. Water expands as it heats up as well, and it increases in volume. So the majority of the sea level rise actually comes from thermal expansion as the water is physically expanding as it gets hotter and hotter and hotter. And this has some severe impacts for us. Remember that the majority of human population is on the coast. For Florida, for example, upwards of 70% of the entire population of Florida is within 10 miles of the coastline. So sea level rise is going to primarily impact coastal systems and coastal communities. Particularly South Florida and Miami will be completely underwater, as you can see in this diagram on the lower left-hand side of your screen. So we're going to have to really be creative with how we combat these issues in the near future, whether we're going to actually have to migrate and move people away from these coastal areas where they currently occupy, or get creative creative in finding ways to keep seawater out from getting into these different coastal communities. So we've already talked a little bit about, particularly in chapter 12 and in earlier chapters, some of the effects associated with ocean acidification. But just to do a little bit of a recap, ocean acidification is basically the tendency of the oceans to get more and more acidic as they absorb more carbon dioxide. Remember again how we talked about how oceans are actually absorbing about half of the CO2 emitted into the atmosphere. They are actually a net sink for carbon dioxide. However, as they absorb more and more carbon dioxide, that absorbed carbon dioxide will react within the water molecules to form carbonic acid. Carbonic acid actually increases the ocean's pH, and basically this means that it contributes to the net addition of H+ ions, contributing to an increase in acidity in the world's oceans. Now, this is a particularly bad problem, again, because coral reefs and several other organisms, basically any organism that builds a shell, be it crabs, crustacea, shrimp, or any sort of bivalve or clam, they all rely on pulling carbonate ions out of the water, out of suspension in the water column, to build their shells of calcium carbonate. When the oceans are more and more acidic, it immobilizes that carbonate in the form of carbonic acid. As the oceans get more and more acidic, it essentially, these organisms lose the ability to pull that carbonate out of the water to build their shells. Now, the oceans have already gotten 26% more acidic in the last 100 years, which is absolutely staggering. Because if this trend continues, not only will organisms not be able to pull carbonate ions out of the water column to build their shells, the oceans will be so acidic that they will actively erode their shells, very similar to the image on your right-hand side, which is basically the result of a study which took shells and deposited them into a water with a acidic pH to the level of which we are expecting the oceans to arrive at if we continue to put CO2 into the atmosphere. Basically, at this level, or at this high of an acidity, this water not only prevents organisms from pulling carbonate ions out of the water to build their shell, but it actively erodes their shells. In fact, in about 45 days, these different shells can completely dissolve into the water column. So this is another reason why we really have to think about innovative ways to reduce our CO2 emissions into the atmosphere. So in addition to all of this, global warming and climate change also have severe ecosystem impacts in ways we might not have actually expected. In addition to increasing or decreasing the ranges of different organisms as a result of the different changes in climate, it also has very substantial impacts on the timing or the ecological timing of migratory animals. And this is a phenomenon known as ecological mismatch or ecological mistiming. Basically, plants and insects rely on temperature for seasonal activities. Basically, once the temperature warms up to a certain extent, plants will begin to bloom and insects will begin to hatch. However, birds or other migratory animals rely on the day-night cycle in order to begin or end their seasonal activity. So basically, while plants and insects use temperature, birds and other migratory animals use the length of the day versus the length of the night to know when to start their migrations. And this is a problem because climate change impacts the temperature, or basically how fast things begin to warm up, but it doesn't actually impact the day-night cycle. So what's happening here is that a mismatch is beginning. Plants and insects are leafing and hatching earlier and earlier into the year, but birds are still arriving at the same time that they've always done because the day-night cycle is not actually influenced by climate change. And as a result, there is a mismatch between when food is available for birds and when they're actually arriving on scene. Even though birds are arriving on time, each year that they arrive, there's going to be less and less food simply because the insects have already molted and have already begun to metamorphosize into other organisms. So basically, they've sprouted wings and become butterflies or beetles or whatever they're going to be or what have you, and the birds are no longer able to find a consistent food source, which is resulting in losses in populations of migratory birds. Regarding agricultural impacts, this is also going to be a bit of a mixed bag. On the plus side, more CO2 means more resources for photosynthesis. On the downside, there's going to be more heat waves, possibly more droughts and extreme weather events, all of which can decrease yields. The likely scenario is that there are going to be winners and losers within agriculture. And basically, there's going to be a dramatic increase in yields in the polar regions, areas like Canada and Russia, which in areas where previously it was too cold to really grow anything substantial, these areas are going to see higher temperatures and longer growing seasons, so their yields are going to increase. However, everywhere else in the mid-latitudes and any place where it's already warm enough to grow food, these places are going to get hotter and hotter and they're going to be subject to more extreme weather events, and so it's going to decrease their yields in those areas. So there are going to be winners and losers within agriculture. agriculture and the agricultural impacts seen by climate change. So to summarize, there are going to be a lot of consequences and impacts as a result of climate change, none of which are really good. There are going to be some positive benefits with regards to agriculture, but by far and abroad, most of the impacts of climate change are going to be very severe. And here's a flowchart that basically has a lot of the problems associated with the impacts of climate change. I encourage you guys all to review them in the PowerPoint slide. I'm not going to go over all of them in particular. A lot of them would kind of just be going over everything that we've already talked about, but this flowchart is very useful in understanding some of the multifaceted problems that we face in the 21st century. Now, this concludes the lecture on the impacts of climate change. In the next lecture, we're going to look at some of the solutions to climate change, both with regards to mitigation as well as adaptation, ways to adapt to the problem of climate change, as well as ways to mitigate or alleviate the problem in and of itself. I look forward to seeing you guys again then. Take care.